So one of the difficult things about learning pymatgen is just discovering all the features and functions that are available in the code. And so what I wanted to do today is to just run through 5 different features that you should know about in pymatgen, and we're going to go relatively quickly through these. And so I'll link the Jupyter notebook down below where you can run things yourself at your own pace if you need to. And as in previous tutorials, we're going to be using the Crystal Toolkit library to make the structures visualizations interactive. All right, so feature number 1 is simulating experimental diffraction patterns. And this can be useful for confirming that you have a particular crystal structure, for example, because you can simulate the pattern that it should have, compare that to the experimental pattern, and determine if there's a match. And pymatgen lets you simulate powder X-ray diffraction patterns, neutron powder diffraction patterns, as well as TEM diffraction patterns. So I'll show you each of those examples, and what we'll do is we'll load the magnesium aluminate crystal structure and then generate the experimental diffraction patterns or predicted experimental diffraction patterns for this structure. So in order to get the structure of magnesium aluminate, I'm just going to load it from a CIF file. This was covered in a few of the other tutorials as well. And with Crystal Toolkit, we can see what the crystal structure looks like. So this is a spinel type structure. The magnesiums are in orange, the oxygens are in red, and then the aluminums are going to be in blue. So let's simulate the patterns of these. We'll start with the powder X-ray diffraction pattern, and this uses a class called XRD calculator. And using the XRD calculator is very simple. All we have to do is to just import the XRD calculator class, give it some parameters of our diffraction experiment, in this case the wavelength of X-rays being used, and then we just call the getPattern function on the crystal structure. In this case, this is that magnesium aluminate structure that we just loaded, and then that will give us an XRD pattern object. And that will have attributes like the X, which are the 2 theta values, the Y, which is the intensity, and these will be normalized so that the largest peak is 100. And then finally, the peak labels for each of those X values, each of those 2 theta values. So if I run this code, we'll see a list of peaks for the magnesium aluminate structure. We'll see the intensity of those peaks, and then we'll also see the HKL value. So this first peak over here corresponds to the 111 plane. Now we can also plot these X-ray diffraction patterns very simply using the code below. I'm just going to use matplotlib, and we are going to plot the X values, the Y values, and over here in the bottom of the code, we're going to just label the peaks that are significant. So I've chosen a cutoff of 5, which means 5% of the highest peak, and we'll label those peaks as well. So if I run this code, what I'll find is the XRD pattern for magnesium aluminate with the significant peaks labeled. The next type of diffraction we're going to look at is neutron powder diffraction, and this is a complementary technique to X-ray diffraction. It's a little bit more specialized of a technique, but it can give you more detailed information about your crystal structure. Now, using this code is very similar to the X-ray diffraction calculator. You just import the ND calculator instead of the XRD calculator. Again, you give it the parameters of your experiment, and then now this object, this ND calculator, can have a getPattern function. You give it the crystal structure you want. Again, this is magnesium aluminate, and then we'll get the X values, the Y values, and the HKLs, just like we did for the XRD calculator. And plotting this is pretty much exactly the same as plotting the XRD calculator. So the code here is shown, and again, we're going to just label the significant peaks, which means 5% of the highest value. So here's a neutron diffraction pattern for magnesium aluminate, and again, that can be compared against experimental data. Now, the final diffraction example is a little bit different. This is from TEM diffraction, and this is corresponding to a method like selected area electron diffraction. And so this is going to give you a 2D plot of peaks. And there's kind of a shortcut way to use it and a longer way to use it. So I'll show like the shortcut way first, and then we'll go through the longer way. But in order to use this calculator, you import TEM calculator, and then the shortcut way is to use this getPlot2D function on your crystal structure, again magnesium aluminate, and then you can just get this plot and customize it to your liking. And this, if you do this, this will give you an interactive plot. So this is the diffraction pattern, the 2D diffraction pattern for magnesium aluminate, and you can actually hover over these points and get the values of the HKL that correspond to each of these dots. Now, if you want to use this in a little bit more detailed way, you can do that as well, where you actually get the data points for the dots and then plot them yourself. So if you want to do that, the code example is here. You basically generate a grid of HKL points you want to check, and then call this TEM dots function to get the positions of the dots as well as their intensities. And then there's some code down here that you can go through that plots those and then labels the HKLs. So if I run this, you'll find that you can now get a TEM plot that has the HKLs labeled by default, and you also have access to the raw values up here in this X, Y, and HKL and intensity values. Okay, so feature number 2 is matching crystal structures and prototypes. Now, because of the nature of 3D crystals, you can find the same 3D crystal represented in different ways numerically using different sorts of lattices, different bases, different settings, etc. And so it can be very difficult sometimes to know whether two different representations of a crystal structure actually represent the same fundamental crystal or not. So pymatgen includes a tool called structure matcher that can be used to match two crystals together and determine if they're the same. And then it can also be used to group crystal structures into prototypes, and I'll demo both of those in this tutorial. So the first thing that we'll do is to actually just match crystal structures and determine if they're the same. And to do this, I'll just demonstrate two different settings of the silicon crystal structure. So there is the conventional structure, and this is what most people think of when they think of silicon. So I'm loading this from a CIF file, and you can kind of clearly see the lattice of silicon here, and the positions are like 0.75, 0.5, 0.25, etc. And the lattice angles are all nicely at 90, 90, 90 degrees. But there are other ways to represent this crystal structure, and in particular, there's the reduced or primitive cell. And if you look at the reduced cell of this crystal structure, it looks quite different. So the angles are no longer 90 degrees, there's only 2 atoms in the unit cell, and it can be difficult to know that this is actually the same as this. So what the structure matcher does is it actually tries to find these mappings between crystal structures. And in order to use it, all you have to do is to import the structure matcher, give it some parameters. In this case, I'm going to set a temp supercell equals to true, because clearly these have different numbers of atoms in the supercell. And then finally, I'm going to try and fit these two structures together. And when I call the fit function of structure matcher, it returns true, which means that these are actually the same crystal structure. Now, in addition to saying that the match is there, you can also get the transformation matrix that is found to match the structures. And the only kind of change to do that is that you have to set the primitive cell value to false for the structure matcher. So if we do that, we can actually call this getTransformation method. So if I do that, it will tell us exactly how do we map this reduced structure onto this conventional structure. Now, by default, the structure matcher ignores small distortions, so I'll demo that here. So if I take the conventional structure and I use this perturb method, which we covered in, I think, part 4 of the tutorials, that will actually take the atomic positions and kind of mess with them a little bit. And so now instead of like 1, 0, 0, and 0.75 and 0.5, you can see that these atomic positions are displaced from equilibrium, and you can kind of see some of those displacements here in the visualization as well. But the structure matcher is resistant to these small distortions by default. So if I use this default structure matcher object and I call fit on the perturb structure with the conventional structure, it will still return true. And that's by design. If you don't like that behavior and you want to be very strict with the way that you do structure matching, you can initialize the structure matcher with different parameters. So for example, if you have a tight version of the structure matcher and you set the lattice length tolerance lower, the tolerance for the atomic positions to be lower, and the tolerance for the angles of the unit cell to be lower, then you can actually do a fit that really is, very picky about the positions being very close to one another. And in this case, the perturbed version no longer matches the conventional cell. Now, another feature is that you can also define the structure matcher so that you don't have to have the same composition in both cells. So for example, if you want to group structures into prototypes and they have different chemical compositions, you can do that as well. And to demo that, I'm just going to load up 2 structures, barium titanate and lead titanate. These have pretty much the same crystal structure, but have small distortions from the perfect cell that are different in each case. But nevertheless, they're almost the same. So this structure 1 looks like this perovskite looking cell. Again, you can see some small displacements here from the perfect perovskite cell. And this second one is this lead titanate. And these clearly have different chemical compositions. You can also see that they're represented somewhat differently because this 2+ ion is in the center of this cell, and that's the one that has 12-fold coordination, whereas the 2+ ion is on the edges of this cell. And so it's kind of the atom positions are kind of shifted between these two unit cells. Nevertheless, we can use the structure matcher to match these. And the default structure matcher, the fit method, is not going to match them because they have different atom identities. But if I call the fit anonymous method, I can actually match crystal structures with different chemical formulas. So if I run this, I can see that the normal fit gives false, but the anonymous fit gives true. And for the anonymous fit, you can also get mapping. So you can say that when you actually match these crystal structures together, the lead site of this structure 2 corresponds to the barium site of the structure 1. Those are the 12-fold coordinated sites. And the titanium sites are going to map to one another, and the oxygen sites are going to map to one another as well. So this can be useful to know exactly, how prototypes are related to one another, or two versions of a prototype are related to one another. Now, going further with the prototype matching, so the AFLOW library released a database of crystal structure prototypes. And what we can do is we can actually take any crystal that we have and match it against the entire database from the AFLOW library and determine which prototype class any crystal belongs to. And so if you want to use this feature, you should certainly cite the AFLOW prototypes paper, which is listed over here. And using this code is very simple. All you have to do is to load up your structure. So in this case, I have my barium titanate structure again. And if I want to know the prototype of this, I can import the AFLOW prototype matcher, load it up, and then call this getPrototypes function. And so when I run this, it's going to take a little bit of time to look up through the library and try to match this structure to every prototype that's in that library. But then it's going to finish and give me the result. So the result is that this is a cubic perovskite type prototype, and there are also some other symbols here like structure barite, AFLOW symbol, and some Pearson labels as well. And so you can kind of get very quickly the prototype class of any crystal structure. And then you could use this, for example, to group crystal structures into different prototype classes. Let's try another example. Let's load up that magnesium aluminate from before. I mentioned before that this is a spinel structure. And so if I call the AFLOW prototypes matcher on this compound, so I'll see that this actually returns a spinel type structure with, again, an AFLOW label, etc. So this can be very useful again for determining exactly the prototype of a crystal, as well as determining which crystals might match to one another in certain classes. All right, so feature number 3 is cost and HHI analysis. And this is to determine if your compound that you're looking at is going to be an expensive compound, or whether it's going to contain like critical elements in it that are geographically confined and may be difficult to source. And so this is a very kind of rough analysis that's implemented in pymatgen. Nevertheless, it can be useful for just categorizing or grouping compounds into like, okay, this is probably going to be really expensive or probably going to be relatively cheap. So the cost analysis is based on data from the year 2013 from a few different sources like Wikipedia and Wolfram Alpha. This is basically what the cost of every element is in this database. So you can see, for example, these platinum group metals are going to be, the highest cost. So what it's going to do is for every compound, it's going to sum up these elemental costs to determine a compound cost. So let's look at a few examples. In order to use this code, we have to import both the cost analyzer and a database of costs. The only one that's implemented right now is this elemental cost database. And so if I initialize the cost analyzer with this database of costs, I can get the cost per kilogram or the cost per mole for any chemical composition that I give it. And there's no structural distinction. It's all just based on the composition. And what we see here is that both SiO2 and Si are relatively low in terms of cost. So this is in US dollars per kilogram or US dollars per mole. There are, again, if you were being nitpicky about this, you would say that, okay, SiO2 can vary in cost a lot depending on its purity and form, etc. And same with silicon. But nevertheless, you see that these are similar in cost and, relatively low. Whereas if you take something with, platinum group metals in it, like platinum gold, that's going to show up as being much higher in cost. So again, it can be useful for doing a rough grouping of compounds into high and low cost. The second analysis is the HHI, and this is a measure of how geographically constrained the elements in a compound are. And so things with a high HHI, like above 2500, may be more like critical in terms of, resource, obtaining that resource, whereas things with a low HHI, like less than 1500, may be, geographically dispersed and relatively easier to source. And there are two sets of HHI data. There are ones in reserve. So these are the amount of elements that are in reserve or were in reserve in 2013. And then there's the production, which is the annual production of these elements. So they can give different HHI values. Now, if we look at something that's relatively, abundant, like sodium carbonate, and compare that to something that is, more critical in terms of resource locations, like neodymium, praseodymium, we're going to see a difference in the HHIs. So for the sodium carbonate, we're going to see relatively low values of the HHI. And for the neodymium praseodymium, we're going to see relatively high values of the HHI. And if you're interested in this analysis a bit more, you should really read this paper that really goes over how to define the HHI and where the data comes from, etc. And then you should certainly cite this paper because that is where the data and the analysis method comes from as well if you use this value. Okay, so feature number 4 is going to be a host of composition tools that pymatgen has. This is for formatting compositions, working with compositions, etc. So the first thing is just basic composition formatting. You can format a chemical composition in several ways. So you can get the composition by calling the composition attribute of a crystal structure, or you can just directly create a composition like so. And then pymatgen has a few different ways of writing these chemical formulas, including the IUPAC formula, an alphabetical version, the Hill notation, etc. And you're going to get different orders of elements and different ways that chemical formulas are formatted here. Note that none of these methods really give you the way that like a chemist might write some of these formulas, like this LiFePO4SO3. None of these really give you that sort of grouping. So you still have to kind of do a little bit of work if you want things grouped in a way that a chemist might do it or a material scientist might do it. Nevertheless, you do get several options, and this reduced formula and factor can take things like a 2:6 ratio and turn that into a 1:3 ratio to kind of homogenize the way that these formulas are written, as well as the factor by which it divided each of these amounts. Now, another composition tool that can be useful is to format the formulas in a way that anonymizes some of the information. So for example, given that list of compositions before, so these are the original compositions here, we can print out just the chemical system, so that will ignore the amounts of every element and just give you like the alphabetical elements in order. So this can be useful to group together compositions that are in the same kind of chemical space. And similarly, you can get the anonymized formula, which will ignore the elements, but will keep the stoichiometry and their ratios. And this will order the elements by, lowest amount to highest amount. And this can be useful for grouping elements together or grouping compounds together. Okay, a third interesting thing you can do with compositions is to quantize compositions. And the best way to demonstrate this is probably to show an example. So if you have a composition that is close, like this is close to TiO2, but it's not quite TiO2, it's like a defective version of it. And so if you have something that's close to a composition, you can use this get integer formula and factor to try and quantize that composition closer to something that you expect. And so if you call this with the max denominator of 10, you will get TiO2, which is going to be the more perfect version of this composition. If you call it with the higher max denominator, it will try to retain some of the vacancy type information that might be here, but it might not be exactly the composition that you want. So depending on the max denominator that you set, you can get things to be more or less quantized. Now, a fourth tool for working with compositions is to work with compositions by mass rather than by stoichiometric amounts. So you can use the to-weight-dict and from-weight-dict methods in pymatgen to do that. So for example, if I have a stoichiometric composition and I want to convert that to weights, like let's say I'm mixing chemicals together in order to create this composition, you can do that. Or you can also take a list of weights and turn that into a stoichiometric composition. So the first one, if I want to see the weight of nickel and platinum in the 1:1 ratio, you can see that there's going to be a higher weight of platinum because it's more massive than nickel. In the second one, you can see that if I mixed these in this ratio, I actually get a 2:1 ratio of tin to silicon. And because this looks a little bit weird, it tries to normalize these values so that they add up to 1. It's unclear maybe exactly what this stoichiometry is. So if you use this normalization tool, this get integer formula and factor from the previous example, you can kind of see that this is actually like an SI-SN2 type phase. All right, so a fifth composition tool is to guess the oxidation states of a composition. And this does basically a statistical analysis to try and figure out what's the most likely oxidation states in a composition. And this is different than the bond valence analyzer tool that we demoed in part 4, because that one used the crystal structure to estimate the oxidation states. This one is just making guesses based on the composition. So here's a few compositions listed here, and if I call the oxy-state guesses of that composition object, it's going to give me guesses for the oxidation state. So let's try this. So this barium titanate material, we can see that it guesses barium is 2+, titanium 4+, and oxygen 2-. That sounds pretty reasonable. You can also get mixed oxidation states. So Fe3O4 is going to have mixed 2 and 3, and it's going to say the average is just 2.67. You can get multiple valid guesses, so because manganese and iron both have multiple oxidation states, it's going to try its best and give the first answer like the most likely answer, which is both of them being 3+, and it'll give a second likely answer, which would be manganese 4+ and iron 2+. If the composition can't be charge balanced like LiO, it's going to basically return nothing. And if you want to, for example, include, let's say, peroxide type compounds where oxygen can be -1, you can override the dictionary of oxidation states in this code. And in that case, you will actually see that you get a charge balance structure where oxygen can be -1. Finally, you can do oxidation state balance with a target charge. So for example, if you have an anion like PO4 and you want it to have an overall charge of -3, you can do that and it will figure out that, phosphorus has a oxidation state of 5 and oxygen has a oxidation state of -2, and that will give the overall target charge of -3. You can also use this feature to add oxidation states to a composition very easily. So if you start with a composition and you want to just add charges to it, you can use add charges from oxy-state guesses, and it's just going to go ahead and decorate the composition with oxidation states. All right, so the final composition tool that I'll demonstrate is using fuzzy formulas. And this is really if you initialize a composition with the wrong capitalization, pymatgen can try to fix that capitalization for you. And this is pretty much only useful, I think, if you're designing a user interface. Nevertheless, if you give it a formula with the wrong capitalization, it's going to try and fix it for you, and it's going to suggest the correct compositions. It's going to try to rank them by how close it is to the original formula that you gave it. So in this case, it's going to say, SiO2 is probably what you meant, but if not, maybe it's a silicon, iodine, oxygen, which is probably not what you meant when you typed this formula. All right, so feature 5 is going to be serializing pymatgen objects as files. So a lot of times you do an analysis with a pymatgen, maybe you've generated a ton of crystal structures, or maybe you have analyzed the band structure and you want to save it for later. All of this can be serialized in pymatgen through what's called the Ensemble framework in Monty, which is installed by default in pymatgen. So we're going to skip over kind of the details of the internals about how this works and just kind of demo how the serialization works in pymatgen. So I'm going to load a pymatgen object. In this case, I'm going to pick a structure, and we're just going to pick that magnesium aluminate structure again. So here I have a structure object of magnesium aluminate, and I want to serialize this. And one note here is that I could serialize this to a CIF file, for example. I could write it back to a CIF file. But the nice thing about pymatgen is that it retains all the internal pymatgen information. So for example, if I add selective dynamics to some of these atoms, or if I added magnetic moments to some of these atoms, that would also be retained in the pymatgen serialization, but it might be lost if I export it to a CIF file. So in order to serialize any pymatgen object, you can just call the .save function on it and give it a file name, and it's going to be in JSON format. The strict equals false just means that it will overwrite an existing file if it's there, so it just removes that protection about overwriting previous files. So if I save this, it's going to save a file on my file system that's called structure.json that contains all the information about this object. If you want to get the information in this structure.json more programmatically, you can call this toJSON function, which again will be available for all these ensemble pymatgen objects. And this is the actual information that's stored in that JSON file when you serialize it. And the thing to note here is that in addition to storing the data inside, that corresponds to the object, it also stores the class of the object, which is a structure, and also the module in which that class is. So it will know when it reconstructs this object exactly what type of object to reconstruct it to. So for example, if I want to reconstruct this object, I can import this load file name or load fn function from Monty. And if I load this fn from the structure.json file that I just exported, it's going to figure out that this is a structure object and properly create that type of object. So if I call this reconstructed structure, we can see that it is actually of type structure because it renders in Crystal Toolkit, and it's exactly the same as the original structure that we had. So just to demo this to show that this is available for more than just Crystal structure objects, I'm going to just import a band structure as well. So this was also covered in one of the previous tutorials about VASP.io. But here I'm going to load a band structure from the VASP software, and I'm going to plot it. And so this is the object that we want to serialize and maybe retrieve later. So just as before, I'm going to call the save function on this band structure object now and save that to a JSON file. And then if I recover that using the load fn from Monty, it's going to, again, correctly determine that this is a band structure object. So it's going to reconstruct it as the proper type of object. And if I plot this band structure, I'm going to get the exact same thing as I did with my original band structure. So if you're ever doing, a long pymatgen analysis and you don't want to redo that analysis every single time, or maybe you're querying things from a database and you don't want to, re-query that database all the time, I would highly recommend just serializing things to files. And if you are saving things in like a MongoDB database, you can use this toJSON method in order to get the data that you can, insert into MongoDB. By the way, there's also a toDict method that can be used to insert things into MongoDB. Sometimes you might want to use toJSON, sometimes toDict. All right, so those were the 5 features that you should know about. Hopefully it gave you more of an idea of the types of things that you can do with pymatgen. I'll see you in the next video.